This video is friction hell. Hi guys, so here's a quick video talking about friction. Hope it'll help you a little bit. We've dealt with moving objects all year, and we've always just kind of said, ignore this thing called friction, it makes things tougher. It's really not complicated, it's a simple idea. You already know it. I'm just going to help you kind of quantify it. So let's take the simplest example. There's a tabletop with an object sitting on it, and this object is going to get pushed to the side. So let's give it a little force here, we'll call it F, push. Great. Well, when I do that, friction is working against me. Friction always opposes motion. It's what we call a responsive force, a reactive force, really a non-conservative force. We'll talk about what that means later when we get into energy and thermodynamics. But if I push this way, I have this force of friction pushing back this way. If I was doing the opposite, friction would be pushing that way. Now, the neat thing about friction too is it can change how much it's pushing. So let's say there was enough friction here that it could push 1,000 newtons, which would be a lot. I would have to push at least 1,000 newtons to get that. If I started pushing on this eraser, and friction could push 1,000 newtons backwards, and I started pushing 10 forward, it's not going to take off this way. It's only going to respond. So right now I'm pushing 1 newton, it's pushing back 1 newton. I'm pushing 2 newtons, it's pushing back 2 newtons. I'm pushing, say, 4 million newtons, and all of a sudden I can get it to move. So there's kind of a point where friction just can't push any further. And what we normally do when we're calculating friction is we calculate that point. What's the most it can push? So there's 2 things that determine how much friction you're going to get. We talked about them in class. The first is texture. My hands are pretty sticky. Creatures have evolved over millions of years to develop kind of sticky or friction-y hands. That's helpful if I want to pick something up, like this protractor. It helps that my hands are sticky because otherwise it would just slide right out of my hand. All right. There's other things that are smooth, like Teflon is very smooth. There's things that are very friction-y because they're sticky, like tape or glue. My hands are kind of rubbery, they stretch a little bit. That makes them sticky or friction-y. It's hard to measure stickiness or roughness or stretchiness. So instead, we don't do any of that. What we do instead is we have this thing we call coefficient of friction. We call mu. That's the Greek symbol mu. It's kind of like a backwards Y, or really it's more like a backwards U with a big long tail. So mu is what we call the coefficient of friction. And what it ends up being is just a kind of ratio between how much friction you get versus the other thing friction depends on, which is how hard are 2 surfaces pushing together. So right now, there's no friction between my hands. There can't be. They're not touching each other, so they can't push against each other. When we first talked about forces and Newton's laws, we said you cannot have a force without some kind of interaction between 2 things. My hands aren't interacting. Put it in front of the board so you can see a little better. My hands are interacting, no friction. Still not interacting, no friction. As soon as they come in contact, though, there's a little bit of friction between them. So right now I can slide my hands back and forth pretty easily. If I start pushing together really hard, it becomes harder to slide them because there's more contact force. The more things that smush together, the more friction there is. Now, we've talked about things being pushed together. An easier way of thinking about it isn't how much is my hand being pushed into the surface of my other hand, or if I use the board. Not how much is my hand pushing into the board, but how about how hard is the board pushing on my hand? Because we've already talked about that force before. We call it normal force, right? Fn. All right. Normal force. And friction depends on normal force. How hard are you being contacted? All right. We're going to write one last thing in here because we're concerned about friction. And I'm going to put it up here because mu is simply a ratio of how much friction you get based on how much normal force you get. Now typically we won't write this way. Typically we'll write force of friction equals mu times normal force. And what this says is, the bigger my coefficient of friction is, or the more frictiony a surface is, the more friction force I get. The harder I'm pushing between two things, the more friction force I got. So for instance, if we look at this problem, and we say, okay, this is a, for simplicity's sake, let's call it a 100 kilogram object. And let's say that this interaction of materials here has a coefficient of friction of 0.4. What's going to happen to the situation, assuming I push, let's say, 900 newtons? Well, let's see. First of all, this is a complicated setup, so let's make a free body diagram instead. There's my picture. I have the force I'm pushing this way, F push. We got friction going backwards. We got gravity going down. And I got normal force going up. Now, I can calculate all these relatively easily. Fg is equal to mass times acceleration of gravity, which in this case is 100 kilograms times 9.8. So the force of gravity is negative 98 newtons. Well, if my force of gravity is 98 newtons, negative 98 newtons, sorry, that's my alarm going off. If my force of gravity is negative 98 newtons, how much is the surface pushing back? Positive 98 newtons. Now, normal force is also a reactive or responsive force. It's responding, in this case, to gravity pushing us into the surface. Okay, so I got normal force, I got force of gravity. F push, I already know, it's 900 newtons. I just told you that. Well, how much is the force of friction? Well, we could simply use our formula down here. Force of friction is mu times normal force. We already said that mu is 0.4, and normal force was 98 newtons. So we're going to get, a number here. I'm not going to do the math out, but it'll be somewhere around like 38, 36 newtons. So I have a frictional force of about 38 newtons backwards, which means the overall effect of everything that's going on here, if I were to calculate my net force, is that I got 900 newtons pulling this way, and about 38 or so pulling back. So overall, it's kind of like I'm pushing forward with 870 newtons. Now remember, net force, I'm running out of room here. We'll go up top. F net is equal to the square root of the sum of forces in the x squared plus the sum of forces in the y squared. Well, in the y direction, the sum of the forces is 0 because 98 plus negative 98 is 0. So that part goes away. The sum of the forces in the x are going to be positive 900 minus, this is going the opposite direction, about 38. So something like 870 or 862, whatever it would be. So your F net is 862. Now this is usually how friction works. It usually doesn't stop things from moving, it just affects it a little bit. So when we roll a cart down a hill, or if we push a block across the desktop, and we don't get really good measurements, we say, man, I expected my force to be 900 newtons, but instead it was 860. Or I was expecting it to be 860, and instead it was 900. A lot of times the reason we get that inconsistency is because we just ignore friction. We pretend it's not there. But it is, always. We can try to make it small by reducing this coefficient of friction, but it's pretty much always there. And one last note for coefficient of friction, two things. One is that it has no units, well, three things. One, it has no units. It's a ratio of forces. Forces are measured in newtons, and newtons divided by newtons is nothing. So the coefficient of friction has no units, it's just a number. Second thing is that it's typically a number somewhere between 0 and 1. If you were to have a coefficient of friction above 1, say 3, what that would say is that friction is 3 times greater than normal force. So if you think about it in this scenario, normal force is 98 newtons. if friction was 3 times greater than normal force, it would mean it's actually easier to pick it up than it is to slide it. I would have to lift 98 newtons to lift it up. I would have to push almost 300 newtons to get it to move. So typically, that doesn't happen. Typically, it's easier to slide something than lift it up. So coefficient of friction, usually between 0 and 1. And it can't be negative because it's a scalar, it's just a number. So negative doesn't make sense. In fact, if you put a negative in, that would mean friction just moves things on its own. It helps motion, which is certainly not the case. Now, last but not least, there's this one little goofy thing about coefficient of friction, that if you try to pull something, so here's a graph, let's say the force of friction over time. Let's say I tied a rope to this, and I started pulling it harder and harder and harder and harder and harder until eventually it started moving. I would see this. Friction would be pulling harder and harder and harder and harder and harder, and then all of a sudden it would drop and it would level out. So there's a reason for this. It's getting bigger here because friction's responding to me. So the harder I push, the harder it pushes. But then it comes to this kind of peak that's a little higher than over here. That's because friction is actually greater when something's not moving than when it is. If you think about friction as a Velcro. Imagine that these are loops and these are Velcro hooks, and I'm trying to slide it across. I'm constantly breaking and attaching one of those connections. But there's never really a time where all 4 are connected. If I'm not moving, and all 4 hooks are attached at once, I have to break all of them at the same time. Now, that's not a perfect analogy, but I think it makes a little bit of sense. When things are still, there's more ability for the surface to grip onto each other, or the surfaces to grip onto each other. When it's moving, it's a little bit more difficult. So the result is you have a little drop in friction between when it's moving and not moving. We call this, or mu here, mu static, for static friction or still friction. And then at this point, we'd be talking about mu kinetic for the friction of movement. So that is one big overview of everything that you need to know about friction. Hope this helped. Bye-bye.